today we're going to continue with our rules of inferences. What are the rules of implication we have learned so far? Right? No, for modus tollens, for modus ponens, that actually doesn't work the other way around. It would be a fallacy to say if P then Q, therefore P, because it doesn't go this way. It would be equally a fallacy to say not P, therefore not Q, because P is not a necessary condition. So you can have not P and Q still would be true. And that also, remember, makes sense, because it will only be false if this is true, this is false. But if this one is false, then that doesn't work. So in this case, there's only one possibility to deny them, and there's only one possibility to affirm. You can affirm antecedent, and you can deny consequent. You cannot affirm consequent, and you cannot deny antecedent. Those are two fallacies. Okay, so these are the four rules, which hopefully you guys already have some idea about. What happened to the picture here? Where did it go? I had a picture. That's strange. Anyway, it's on the slides from the previous lecture, and it's on the board right now. Now, constructive dilemma. We will add four more today. One of them is constructive dilemma. Let's see what specifically we can figure out from even what we have already. Because before we even learn the constructive dilemma, I want you to just understand how it works. It's basically a combination of two modus ponens. So if we have something like this, if P then Q and if R then S, then that's our first premise, right? And the second premise that it is either P or R. Now, if you look at modus ponens, if P then Q, P would lead to Q, right? So if P then Q, P would lead to Q. Yeah. And if R then S, R would lead to S. So that's the constructive dilemma to you, because that would then mean that one of these two should be true. So that's basically the idea behind the constructive dilemma. Yeah, so this is the four rules of implication, which we already saw. This is the dilemma, constructive dilemma. Okay, great. And this is an example of constructive dilemma in language, right? If Oscar is a dog, then you'll have fleas. And if Oscar is a cat, then you'll have fur balls. Oscar is either a dog or a cat, so you'll have either fleas or fur balls. A little pessimistic, but yeah. So you see, that's the same thing in words. If P in this case, then Q. If R, then S. So if it is either P or R, then you will have either Q or S. And it is again based on the idea of combination of modus ponens and disjunctive syllogism, because it gives you two disjunctions. This is some examples of constructive dilemma, as you can see it in propositional logic. Well, in this case, the order of premises is reversed, but remember it's the same thing, right? So if you have something like this, you can see that this is the same as if P then Q, if Q then R, and in between, then they again give you a choice of one of the two antecedents, which leads us to obviously one of the two consequences. Okay, now you can also have a destructive dilemma, but it actually is not considered necessary to learn separately. What exactly is destructive dilemma? Well, let's take a look here. We can just apply the same logic but using modus tollens, right? So we would then, if we are using modus tollens, what are we going to get here? So if in the previous case we had P or Q based on modus ponens, what do you think we will have based on modus tollens?
Q. Oh, no.
It has to be a negation, right? So not Q or not S.
Okay.
So you either negate, because you see that here you are negating your consequent. So here you are negating your first consequent and your second consequent, and that would then lead to what?
P
Look
or-
here, think about it.
Not Q or
Not P or not R. Because again, you have a negation there, right? And that's why it's called destructive dilemma, because it can destroy, right? It puts negations there. You put negation, you destroy it. So, by rule of transposition, which we will learn in 7.4, there's really no need for that, because it is obviously follows from the other rules anyway. But just so that you would know, this is a destructive dilemma. Okay, now next rule is a rule of simplification. Simplification just says that if you have P and Q, you obviously will have P. Right? That makes sense, because remember that P and Q would only be true if both of them are true. So if the whole thing is for some reason true, then obviously it would also be equally true that each part is true. You don't necessarily even need the second part. And vice versa, like it means Q, you can have Q by itself. So that's the next rule. In language, that would sound something like this. Eliza has long legs and runs fast. Therefore, Eliza has long legs. So obviously, yeah.
How would we know if they're both true?
No, but that we don't have to know that, right? But to preserve the truth. Because remember, we are now preserving the truth. And to preserve the truth, we can do this operation. Remember that we're working with a longer argument, assuming that it is valid, or assuming everything is true. What next operation can we do to preserve validity? So to keep our truth trickling down with no problems. And here we will have no problem if we do this operation. Now, of course, if something is not true to begin with, then we have a problem, but that's a different type of problem, because we're working with structure, not with the meaning. Remember, this is syntax, not semantics. We're done with semantics for now. And with syntax, we only worry about the structure. If structure is truth preserving, that is all we care about. And this is a truth preserving structure. If we had truth on that line, the truth will still be on the next line. Okay, so simplification just states that if two propositions are given as true on a single line, if they are given as true, then each of them is true separately. Now, if they are not given as true, then obviously the whole thing simply doesn't apply. According to the strict interpretation of the simplification rule, only left-hand conjunct may be stated in the conclusion. Once the commutativity rule for conjunction has been presented, in 7.3 we will see that they are actually equivalent, right? So even though it's only coming up in 7.3, I can already tell you, and I did tell you before, so since that and that can be anything, P and Q is equally equivalent to Q and P, so we can just as well put Q here instead of P, but we just don't have to spell it out, because we already know that. So for our purposes, we only need to write this. This is some examples of simplifications. Again, you see, once you have a quadjunct dot as your main operation, you can repeat just half of it and just drop the other half. And that's a valid operation for all of them, as long as indeed this is a conjunct. But don't make a mistake of, for example, picking out this part, because this is in brackets, so that whole thing is your P. You can't just split it. But you can take this whole part, or you can take this whole part, because, as I said, it is actually interchangeable. Which one's left, which one's right, doesn't really matter. Now, conjunction. Conjunction is kind of easier to understand, I guess. So if you have P on one line, and if you have Q on any other line, and they don't have to go right underneath each other, right? They could be anywhere. You can then conjunct them as P and Q. Because again, assuming each one of them true on its own, of course the connection with the conjunction would also have to be true. Here's how it works in language. Roxy has big eyes. Roxy has tail. Therefore, Roxy has big eyes and a tail. Conjunction just states to us that two propositions, for example, H and K asserted separately on different lines, may be conjunct in a single line. And they can be conjunct in whatever order you choose. So if for your purposes somewhere else Q goes first, P goes next, but you want to put it as P and Q, you can do that. It doesn't have to be, this order of the lines doesn't matter, we already know that. As long as they happen to be somewhere on previous lines, that is good enough. This is all conjunction, so imagine on one of the lines you have not E, on the other line, remember there could be many lines, you can pick it from anywhere, right, as long as it's previous to this. So if you had like 15 lines, not E was somewhere over there, not G here, you can still put another line with not E and not G because they happen to be there. Similarly, not just with single letters, but if you have this and if you have this, you can conjunct that. You have more complicated stuff, you can conjunct them. So whatever you have on one line and on another line, you can just connect it with a dot. Just make sure to, if it's something like this, put brackets there so that you would see that this is one thing. Otherwise, you wouldn't know what's your main operator. And finally, addition. That's the last rule we're learning today. It may be a little harder to understand. So if you have P somewhere, by the addition you can also assume that it is P or Q. You may say, where did the Q come from? Well, remember that strictly speaking, again, that is true preserving because your P is presumed to be true, and that is enough for this whole thing to be true regardless of whether your Q is true or not. Sometimes it is a useful operation, even though we are like sticking something which hasn't even been there before. But important thing to understand, you cannot do this. That is not allowed. That would be a violation. So you cannot conjunct with something which you didn't have before. But you can disjunct. So here's an example. Tail has spots, therefore tail has either spots or stripes. So if you think about it, that is true. If tail does have spots, and it is absolutely true, it also will be true to say tail has either spots or stripes, even if he doesn't have stripes. Right? Okay. So addition just states that whenever a proposition is asserted on a line by itself, it may be joined disjunctively with any proposition we choose. If G is asserted to be true by itself, it follows that G or H is true, even if we never had H. Maybe somewhat puzzling at first, but like I said, if you actually think about it, you'll see that that is a proper step. It is allowed. But don't use it with conjunctions. That is not allowed. So only disjunction. There are some examples here. If you had S, you can also say it is S or not T. Where did not T came from? Well, you may need it for whatever reason, right? Like if you write in proof, you may have this somewhere over there, and or you may have some other thing there, which this would actually work using some of the rules. And that is allowed. There's no reason why it's not allowed. Similarly here, maybe adding something even more complicated or even more complicated, as long as the wedge is your main operator, you can do it. Okay, so let's look at some examples how these rules can be applied, because we're again going to be doing the same thing as we did last time, except now where we have more rules, so more tools in our box to reach our conclusion. You see, again, we are starting with what we are given. This is the argument we have. Exactly.
Lines 1 and 3.
Exactly. Between 1 and 3, if we use MP, we are going to get B. Now, before that would not be very useful to us, but now we can use one of the operations we just learned to get where we actually want to get, which is what? We can assume B or C, right? That's actually addition. It's used on 2, no, that's used on just 4. We're doing just 4 because we don't use any other line, and this is addition. See, that now is useful for us. Why? Because based on that, we can get what? D and E. You see this and this together, 2 and 5, using MP, now gives us D and E. Lovely. And remember, there's another rule we now have, so we can pull the D by itself. What's this rule? Simplification. Exactly. So 6 based on simplification will give us what we are looking for. Just D. That's our conclusion. There we go. We have reached it. You see? That's why these rules are helpful. More rules, of course, does make it a little more complicated because you have to remember all of them, but it also helps us to achieve what we need to achieve, even now with the previous 4 that would not be possible. And remember, like, that question was very good, because you may not understand why are we doing this. We're doing this because we are showing that this structure is truth preserving. Assuming that we had the truth at the beginning, we would indeed reach the conclusion validly in this argument. Now, we don't know if there was a truth in the beginning or not, and we don't care. For the purposes of the structure, we don't care. But if we did, that would still be preserved. The idea is to think through it yourself. So you hopefully can see what we are doing. In the homework, you can try one way. If you don't reach what you need, try another way. It gets it more and more complicated when you have more elements, but it still is not very complicated. And it can be done. It can just be a little time consuming because the more rules you have, first of all, you have to remember them. And second of all, you may go down the wrong track and not actually get where you want to get, even though you're using correct rules. Because in the end of the day, you still need to think about end goal. What are you trying to achieve in each case? If you want to get here, right, so you have to figure it out. We did with constructive dilemma here get L and T as their consequence, so we can actually use K and M, which we have here as our second line, and that will give us our result. Okay, there is another example. Let's see if we can do it ourselves. So, first one. Okay, so again, you can use a variety of different rules to get to this result. What could we go for the next line? Let's just see, like, what options do we have? one option we could simplify, have not m, or we could have n. The other option, we have,
I have a question.
yeah.
How are we gonna get T if there's no T?
Well, you see, that's one of the rules, right? If we get S on some of the lines, if we do get to S, we can have T. Let's see. So S is here. To get to S, we need to get this. How can we get not T and Q? We need to get not P somewhere. To get not P somewhere.
We have to get not m by itself, so we can.
Okay, not m by itself. We can get not m by itself right here, because that already is possible. So not m, right? That would be
Line one
simplification. We have, so now we can get not p. You see that the next line would be not p, and that would be 2 and 5 Stolens. Now once we got not P, we need not P and Q. And we do have Q.
But then we could get.
Because if we get not P and Q somewhere, we got Q. That's what we need.
We can get Q off of line 4. And
Okay.
using just NP.
Right. So this is the simplification of line 3. Once we got Q here, we can combine it with not P. Actually got there because that with this gives us S. But remember that we can validly from S, room here, get to S or T. Because if it is true with S, it's also true with S and T. Even though we don't have T, that rule allows us to do it. Yeah.
From line 7, I got Q using lines 4 and 6. And
What do you mean? From line 7 you got,
like to prove line 7 to Q. I use lines 4 and 6 to get line 4 and 6 and NP to get Q. So I don't know where the 3 and
4 and 6 cannot give you
Using what
Q.
rule are you talking about?
You can't just use this side. 4 and 6 cannot give you Q.
Oh. So how do we get to Q? 3 and 5 using which one?
Because we got 3. And we just simplify. We're eliminating out.
Oh, okay.
Anytime you have a conjunction, you can just pick one of them. So that's how you can come up with T. T is, in this case, completely arbitrarily added, but remember that according to these rules, if you have S, and S is true, S or T will also be true no matter whether T is true or false. So that does lead from that. You can add anything there as a disjunction. Okay, so just some of the strategies the book goes over. If the conclusion contains a letter that appears in a conjunctive statement in the premises, consider obtaining this letter via simplification. So in this case, you get straight to it. If you have C and B, that's already C. So if your conclusion is C, that's very obviously immediately C. Right? Can you see what they mean?
Mm-hmm.
Another strategy, if the conclusion is a conjunctive statement, consider obtaining it via conjunction by first obtaining the individual conjuncts. So in this case, if on one line you have B, on another line you have not C, and your conclusion is B and not C, that's just conjunct immediately. Then we have a long thing here, but that can also be used in a longer one. Because these rules are very useful. They obviously make a lot of things possible. Not everything, but a lot of things. If the conclusion is a disjunctive statement, like B or D, consider obtaining it by a constructive dilemma or addition. So, constructive dilemma or addition. We need to get B or D. They're using line A or C and B to get A or C, therefore B or D. And that's basically all we need in this case. What else? If the conclusion contains a letter not found in the premises, addition must be used to introduce that letter. This is what we did over here. And so we ended up with addition giving us a letter which we did not have before. Conjunction can be used to set up constructive dilemma. That's another possible strategy. We needed the B or D here. So we have if A then B and we have C then D. So we can conjunct them. We can say if A then B and if C and D. And then based on B or D, we can get, based on A or C, which we already have, we can get B or D. So this is just some of the useful strategies which can be employed when you are trying to so typical misapplications. What can sometimes happen? This is what you should not do. The one thing, you cannot simplify picking it out from something like this, right? Because this is, strictly speaking, not a conjunction. This is disjunction. And in disjunction, you cannot just pluck one S out of it. Also, well, we already mentioned it, K is not equivalent to K and L. You can use K or L as addition, but not M. M or N, M. Well, that's going the other way around. You also cannot simplify like this, just erasing one of the sides, right? If you have a disjunction, that is not allowed. If you have a conjunction, that would be allowed, but not disjunction. You can't just stick something inside one of the sides in your conditional either. That also is improper way to do it. Well, basically the idea is everything which we didn't talk about as proper would be improper. There's a few other variations. If L then M, if L then N is not equal to M or N. You cannot assume that this has to be the two consequences. Not P and Q. This is one of the mistakes students sometimes make. They try to do it like math, right? So just keep in mind that if you have something like this, in math, you would think that it is equivalent to this, right? In math.
Mm-hmm.
But it's not in logic. You cannot do this. That's not equivalent. You cannot just distribute your negation. Because if you think about it, you will then violate the rules. So that cannot be done. Equally, this cannot be done. You cannot distribute your negation inside the parentheses, whether there is disjunction or conjunction.